Hi everybody, hope you're all having a good day today so far. Today we are going to talk about linear combinations. Linear combinations are linear combinations of vectors. So of course we're going to be in a vector space and we'll just use the generic letter V for that vector space throughout. So I won't keep saying, well, V is a vector space, we're in a vector space. We'll just assume that throughout. And of course, the vector space will have the operations of vector addition and scalar multiplication, plus and star we'll use for those. And what we're going to talk about today and develop will be linear combinations of vectors, the span of a set of vectors, and the subspace generated by a set of vectors. Now it'll turn out, in fact, that the last two of those items, the span and the subspace, are really the same thing, just looked at from a different perspective. So we'll see that as we go along. So let's start off, as we often do, with a definition. And the definition is linear combination. So we're going to say that a vector is a linear combination of vectors of n vectors v1 to vn in the vector space if there are scalars such that that w vector is the vector sum, the vector addition of scalar multiples of the vectors. And so that's really the simple way to think of it, is that a linear combination of vectors is just vector sum, vector addition of scalar multiples of vectors. And we call the linear combination a trivial, or maybe you should say the trivial linear combination if all of the scalars are just zero. And of course it's obvious that then the trivial linear combination gives us W vector as the zero vector. And so the trivial linear combination is kind of unique. There's only that all the coefficients are zero, all the scalars are zero, and we get the zero vector. And if any of the scalars in that linear combination is not zero, then we say it's a non-trivial linear combination. And so you should note too that while if all the scalars are zero, so we have the trivial linear combination, we certainly get the zero vector. Things can go the other way, but they don't go the other way quite the same, in that we could get the zero vector as a linear combination of vectors, but a non-trivial linear combination. Just take the simplest, most obvious example would be if there's only two vectors, v1 and v2, and v2 is the negative of v1. So then if we take 1 times v1 plus 1 times v2, which is the negative of v1, that's a non-trivial linear combination. And of course, that linear combination gives us again the zero vector. One other thing we should point out here, perhaps, and maybe I should write this down, is that the number of vectors here, the number of vectors vi, the vi's, is finite. So we don't talk about linear, we don't define linear combination of an infinite number or an infinite sequence of vectors v1, v2, v3, and so on. The number of vectors that go into a linear combination has to be finite. It could be large, it has to be finite, and the number of vectors has to be a natural number. And so let's do one more definition before we look at a somewhat extended example here. So here we have the span of a set of vectors. So S is a set of vectors here, and the span of this set of vectors is the set of all of the linear combinations that we can form from those vectors. So in other words, we fix the set S of vectors. Let's suppose for a moment that it's a finite set. It's just v1 to vn, let's say. And then we look at all of the different scalars that we could put in to get to get a linear combination of those vectors. And that set that we get is called the span of the set, and we denote it by the script L of S. But that set S doesn't have to be finite. S could be an infinite set. S could be the whole vector space, in fact, because it can be any subset of the vector space. And again, the span then is the set of all linear combinations, but the linear combinations are made up of only a finite number of that perhaps infinite set of vectors in the set S. So that's the idea of the span, and we have this script L of S as our notation for it. And then you'll notice that we say that the span of the empty set is simply defined to be the singleton set consisting of just the zero vector. So that, I don't think we could derive that from the rest of the definition exactly. So that's a kind of a convention that we define because the span of any set of vectors S, we want to have defined. And of course, the empty set is a set, so it's a subset of V. So we simply say that the span of the empty set is just the zero vector alone. And we'll come back and see the role that plays a little bit further ahead in the lecture here. So now, with that, let's take this off, and let's look at an example. So in our example here, we're going to have, to start off with, just two vectors. So there'll be two vectors, V1 and V2, but I'm actually going to use a different letter than V. I'm going to use R, and so I'm going to use R, and I'm going to use a superscript. R1, let's say, is the vector 3, 1 in R2, and actually we might want to write that as R11 and R12, and that's the reason I've used the superscript here instead of the subscript that I've used over here in the definition, because now we're going to be not in an arbitrary vector space, we're going to be in R2, and I'm going to want to sometimes talk about the components of the vector. And while I could use just double subscripts, that would be okay, I just think it might be a little more clarity, a little less confusing maybe if I use a superscript for the name of the vector and the subscripts for the components as usual. And so let's let R2 be the vector 1, 2, and again, that would be R2, 1 and R2, 2. And of course, all of this is occurring in R2. So that is a couple of vectors. And so let's now draw a little diagram, and we'll see these two vectors, and we'll see what the span of a set of vectors looks like. So let's draw ourselves a diagram here. And so here we'll have, and I'm just going to use x1 and x2 as generic labels for the components, but of course the components of the specific vectors R1 and R2 will be R1 and R sub 1 and R sub 2. So we have, and let me use a different color here. Let's first mark off some units. Let's say this is 1, 2, and 3. So 1, 2, and 3, and here, let's say this is 1 and 2 and 3 over here. And so the first vector, 3, 1, of course, that's here. And the second vector, 1, 2, that's here. And so now I am going to construct some very simple sets S. And so let's let S1 be the set consisting of just R1. And so now let's see what is the set L of that set S1. That is the set of all linear combinations of a single vector. Well, of course, it's just all the scalar multiples. I just have V1, in this case R1, and I look at all of the alphas that I could use to multiply by that. And of course, that would be everything on this line, and that would be the positive scalars multiplied by R1. In fact, let's even point out here that this is R1 and this is R2. So that's all the positive multiples of R1, and then of course it goes on in this direction, the negative multiples of R1. So this line through the origin is the set of all linear combinations of a single vector. So it's L of S1, and so let's point that out here. This is L of S1, and now let's let S2 be the singleton vector consisting of just R2, and let's look at L of the set S2, and of course that's going to be the set of all multiples, positive or negative, of the vector R2. And so let's point out then that this line is L of S2. So the first two examples of the span of a set couldn't be simpler, and of course that's because in each case the set was a singleton set, just one vector, so I just had all the multiples, all the scalar multiples of that vector. So now let's look at the linear combinations of the two vectors. So now let's look at the set, we'll call it S12, just to give it a descriptive name, and let's let that be the set consisting of the two vectors, R1 and R2. And now at this point, I want to start couching the example in terms of an application. So the reason I've used R's for these vectors is that I want to think of them as the possible returns to some security, let's say, a bond, a stock, some kind of secure asset. Doesn't have to be a stock or a bond, some kind of asset. And this is a vector of returns that has only two components. And so what do we mean by this vector of returns? So the idea here is, and this application that I'm going to describe is a central application of the ideas that we're developing here in economics, application to the economics of uncertainty, financial economics. And so, as I said, we're going to think of the R vectors as vectors of returns, and the two components are going to be described as state-dependent returns. So the idea here is that there is some uncertainty about the future state of things, about what will happen, what will transpire in the future down the road. And the securities return different amounts depending on what state actually occurs, what state actually unfolds. When the uncertainty becomes resolved, what the state will be. So for our purposes here, we could to be concrete, we could think of the two states as, let's say, the Republicans control the government after the next election as state one, and the Democrats control the United States government after the next election would be state two. So in the US, those are the only two reasonable states, so we could take that to be the entire description of the possible states in terms of control of the government. But of course, there are lots of other dimensions to lots of other kinds of uncertainty. We could have more parties than two, which would give us more components because there would be more possible states that could happen. There could be different states of the weather at different points in time. There could be different states of technology at different points in time. So of course, the actual number of states is uncountably myriad here, but we're simplifying to just take a simple example with only two states, and we'll call them state 1 and state 2, the two possible states that could occur. And so each of these two vectors, R1 and R2, is a vector of state-dependent returns that come from some security. So security number 1 gives us let's say $3. It could be $3,000 or $3 million. Keep it simple, let's just say $3 should state 1 occur and returns only $1 if state 2 occurs. This other security returns $1 if state 1 occurs and $2 if state 2 occurs. So this is a standard central application of all the ideas that we're going to develop today, and for that matter, going forward with vector spaces. Not the only application, but a central application in economics. So if, let's say, an investor uses only one security, he just, let's say, holds security 1, but he could hold lots of units or not very many units. I'll leave the negative units for a moment. If he could hold only positive units, he would be able to get a vector of state-dependent returns that would be a multiple of R1. If he were to hold just the other security, he would be able to get a vector, a state-dependent vector of returns that would be a multiple of R2. And so now let's look at the set of all linear combinations of vectors in this set of these two vectors, and I'm going to use a Z as the name of the linear combination, and I'm going to use H's as the scalars. So this would be a typical generic linear combination of these two vectors R1 and R2 of vectors in S12. And in this expression here, I've used different letters all the way through, but I'm using letters that capture the economic interpretation. So the R's are playing the role of the V's over here in this definition, and they are the two vectors of state-dependent returns to the two securities. The H's are the holdings that an individual consumer or investor might have of the securities. So H1 tells me how many units of the first security, let's say an investor holds, and H2 tells me how many units of the second security an investor holds. And so that's the reason for the H's. They're both scalars. They're both real numbers. The two R's are vectors. The Z is playing the role of the W. So the Z is a linear combination of the state-dependent returns vectors. So all the Z's that we could obtain with various scalars, various holdings of the securities, all the Z's we could obtain would be all of the linear combinations of vectors in S12. And so that would be the span of this set. Now let's say a couple of other things here. One is I kind of brushed off the idea of negative scalars here. So what if one of the scalars were negative? Then that would represent in our application an investor, let's say, having a short position in that security. So he would hold a negative number of the securities would be one interpretation in the application. And so an investor could have a long position holding the security or holding a negative amount of the security. And another interpretation would be that a negative value of H could be someone who writes the security, so issues the security. Someone else buys it and holds it, but the person who issued the security then owes the amounts represented by the security, so he would have a negative holding of that same security. So we can think of the negative H's in either one of those two ways. And so let's see what the set L of S12 looks like over here. So let's note that all of the positive linear combinations, where they're just positive holdings, that would be all of the things in this sort of cone-shaped region. Here's the reason: because we could hold some multiple, let's say positive multiple, of the first security. Here I've got roughly 1.5 units of the first security, and then I could add to that some positive multiple of the second security, which would go out in this direction, and so that would give me anything up here. And similarly, I could hold some positive amount here, then some positive amount of the other one, and so that means that all of the vectors in here would be, well, that would be part of L of S12. So L of S12 would include all the vectors in this sort of cone-shaped region. And in fact, we even use the term cone for this region. That's not something we're going to do right now, but probably later in the course we will see the concept of a cone in a vector space. And it would be just exactly what we're seeing here, this cone-shaped region. And so if we now look at just the negative holdings, reversing this, we would get all of the things down in this region. But of course, we can also get vectors in here and here by taking a positive amount of the first vector and then coming back with a negative amount of the second vector. Or we could take a positive amount of the second vector and a negative amount of the first vector. So it's clear, intuitively at least, that L of S12 appears to be all of R2. It appears that we can get any vector z in R2 by just holding the right amounts of the two securities, choosing the right scalars, H1 and H2. So, L of S2 isn't just this cone-shaped region. L of S2 is actually, or L of S12, sorry about that. L of S12 is R2. And so intuitively that seems right, but let's see if we can verify that. Let's just check out how we would show analytically that indeed the set of all z's that I could obtain, the set of all linear combinations of these two vectors is indeed all of R2. Now, this is something that you've probably done pretty much the same kind of thing before, so as this sort of review, although, again, I want to frame things as we go along in terms of this economics application to the economics of uncertainty, let's say, or financial economics. So let's see if we can, how we can do this. Let's write our vectors as column vectors, and I could write them as row vectors like I did up here, or I can write them as column vectors. So let's write z as z1, z2, and we know that that z is going to be h1 times r1, and I'm going to write the r1 vector first and the scalar second, just because of what I'm going to do with them in a few moments. And so I'm going to write the r1 vector, which is 3, 1, and then multiplied by h1. I could put the h1 in front or the h1 behind, doesn't make any difference since it's a scalar. And then I have the r2 vector, which is 1, 2, and the scalar h2. But when I write it that way, and that's the main reason I wrote the vectors as column vectors, when we write it that way, we can see that this is really the product of the matrix consisting of the first vector, r1 is the first column, and the second vector, 1, 2, r2, as the second column, times the vector h1, h2. And so these components, well, in fact, let me just go a little further and say I'm going to write this as r, h. Now that r is not this r here. This r is the special r real numbers. This is just capital R that I'm using for the name of the matrix. And in fact, I'll even write that. Let's write that off here. Let's just say R is R11, R12, R21, R22. And so that's why I've used capital R. It's just the matrix consisting of the little lowercase r's. And so what I want to be able to establish or find out is whether it's possible to get any vector z in R2, any vector z in R2, any z1, z2, by taking this linear combination of these two particular vectors here. And of course, the answer to that, we know, is that I can do that if I can invert the matrix R, if I can kind of invert the equation. So I can actually solve for the holdings that it would take to get me a vector z if I could solve the equation this equation up here, and the solution would be R inverse times z. So if R is invertible, if R is non-singular, then indeed I can solve for any z vector in R2, and that would tell me that indeed my intuition was correct, that these two vectors span the set all of R2. So in this definition of the span, script L of S12 would indeed be all of R2. So let's actually, so this is kind of known. I mean, you kind of know this, so this is not a surprise in any way. But let's just go a little further with it. And let's see. Let's first start out with taking finding the determinant of R to see whether it's non-singular. I mean, this is such a simple one that you can just look at it virtually, see it's non-singular. But let's just note that the determinant of R is 3 times 2, that's 6, minus 1 times 1, which is 1. So the determinant is 5, and that is not 0. So that tells me, and let's take this off of here right now. That tells me, I'm probably going to need this space here. That tells me that that indeed the matrix R is non-singular, it has an inverse, and I can do this. This is legitimate equation. And so for any z that I want to get, I can solve for the holdings that it would take to give me that z. But I'm actually going to go a little further and carry this out and then look at a numerical example just to follow this through, again, using the application of securities, economics of uncertainty, financial economics here. So let's do some of that over here. So I'm going to take off our definitions over here, and let's see what we want to do here. We want to, well, let me just write in the inverse of R, and I think we can actually do that down here. So I may be able to get away with doing some of this down here. So what is R inverse? Well, R inverse, for these 2 by 2 matrices, the inverse is really easy. So let's just write it like that. And so the inverse is going to be 2 and 3 and minus 1 and minus 1 divided by the determinant in each case. And the determinant's 5. So this is 5, 5, 5, and 5. So that's the inverse of R. As I said, easy to get the inverse of 2 by 2 matrices. And so with that as the inverse, we know that, and now I will come over here, I think. We know that we can write H. So let's put this here. We have H1 And H2, the vector H, is R inverse times Z. So that's going to be 2/5 times Z1 minus 1/5 times Z2, right? So minus 1/5 times Z2. And H2 is going to be minus 1/5 Z1 plus 3/5 Z2. So this tells me actually how to get, just as this did, but here it's a little more detail, how to obtain the holdings that I'm going to have to achieve any particular Z vector, like let's say this one or this one, in R2. And so let's just go one step further with this numerical example here and actually put in some numbers for Z. Let's say that what I want to do is I want to obtain the vector Z equals Z1. Well, I don't need to have it as a, well, I'll write it as a column vector. And let's say, so I want to use Z's that are divisible by 5 just to make the numbers work out nice. So let's suppose the Z's are, let's say, 10 and 15. Right? So 10 and 15, well, that's probably off the screen. 10 is maybe over about in here, and 15 is probably up above the screen here. That's the Z I want to obtain. And so to do that, I simply need to have H1 be 2/5 of 10. That would be 4 minus 1/5 of 15. That's 3. So H1 has to be 1. And let's put H2 down here. H2 has to be minus 1/5 of Z1. That would be minus 2. And Z2, Z2 has to be minus 2 plus 3/5 of 15. 3/5 of 15 is 9. So this is 7. So it tells me that if I want to achieve the returns 10, 15, 10 in state 1, let's say if the Republicans should control the government after the next election, and $15 should the Democrats control the government after the next election, I'm going to have to hold 1 unit of security 1 and 7 units of security 2. And so, and let me point out, by the way, that I don't just go and then get the securities. I mean, then I have to buy, presumably I have to buy from someone those securities. So the fact that I would get 10 units in the one state and 15 in the other state will tell me how much I want to be willing to pay for the 2 securities. And we're not going to work that out in detail, but you can see how that would come out. And so let's just check and see that that actually is correct here. So if I have H1R1 plus H2R2, that's going to be 1 times R1, which is 3, 1. And again, I'll write it as a column vector here. Could write it either way. And plus 7. Whoops, that's supposed to be a 7 there, folks. And this is times 1, 2, because 1, 2 is the R2 vector. And that's going to be 3 plus 7 is 10, and 1 plus 14 is 15. So I indeed get what I wanted to get. And of course, that's R1, and that's R2. So this is just to take a simple numerical example that has important economic content and use it as a kind of a vehicle to see what's happening with our notion of the span of a set of vectors. Now, I'm going to take some of this off, and we'll come back and we're going to extend the example a little bit by adding one more vector and see what happens.